Okay, today's speaker is Toni Annala from the University of British Columbia. So we overlapped there when I was doing my postdoc, I think 2 years ago. And it's great to have him here. And he's going to tell us about topologically protected vortex knots and links.
Okay. Thank you for the introduction. Yeah. So this is some work that I did during my national service in Finland. So oddly, I could do it in a physics group. And yeah, so I'm going to explain what topologically protected knots and links are, but we will start with some historical motivation at first. So around 150 years ago, this Lord Kelvin, who then was known as Sir William Thomson, hypothesized that atoms are just like knotted vortex loops in ether. So, you know, ether is some sort of, you could think of it some sort of like ideal fluid, and then these vortices are there, and if they're sort of knotted, then it is a mathematical fact that in certain kinds of ideal fluids, if you have a knotted vortex, then in the evolution of the system, this knotting type does not change because the cores are not allowed to pass through each other. So this was the mathematical basis that led Lord Kelvin to this hypothesis. And I mean, of course, this is completely wrong. Atoms are not like this at all. However, this was the first main motivation for the study of knot theory. And moreover, it has led to some other interesting conserved quantities in like fluid mechanics and so on. So that's like a sort of prehistory. But now in recent times, the dynamics of knotted vortices in real fluids has been studied in many studies. And what is observed there is that even like very small amount of dissipation, something that would not be sort of there for either for some reason, but this dissipation is enough to cause spontaneous decay of tangled structures via reconnections. So you can imagine that you have this is like the core of a vortex in some sort of fluid, and you can imagine that here the two strands get like closer and closer together, and then they collide, and then they connect in a different way, so that the knotted vortex transforms into this vortex here. And as you can see, this is the unknot. The knot structure is destroyed. So it is then sort of a natural question to ask that if there is knotted vortex structures or linked vortex structures that would be immune against decaying in this fashion shown here. And indeed, this is the main goal of this talk. We're going to present several physically realizable examples of this kind of structures. And these examples are tied from non-Abelian topological vortices, which I'm gonna explain next. So the important thing here is the sort of notion of ordered media. So this is like a useful way to mathematically describe many condensed matter systems. And it basically has 4 ingredients. So you have a topological space X, which is the physical extent of your system. So for this talk, you can just take X to be like R3, 3-dimensional Euclidean space. You could think it's like the whole world, or maybe it's just some small open ball, which is homeomorphic to R3. Then the second ingredient is another topological space M, which is the order parameter space of the system. And now this M depends on the physical substance that fills the system. I will give some examples, I think, on the next slide. The third ingredient is a closed subset C in X. So this is some points in the physical extent of the system, which is called the core of the defects. And the fourth ingredient is a continuous map from the complement of the cores to the order parameter space M. And this is called the order parameter field. So basically, the core, or the C, the cores of the defects, those are basically the locations where the order parameter is not well defined. So let's just give some examples. So I guess the most easiest one is like the Heisenberg magnet order parameter, where the order parameter space is just the two sphere, which corresponds to like unit vectors in R3. And you can think that it corresponds to the local magnetization axis of some ferromagnetic system. So you have some spatial extent and then of a physical system, and then for every point you have some small magnet, and we just record the magnetization axis. Another order parameter space, which is slightly more interesting, is the one of nematic liquid crystals, or uniaxial nematic liquid crystals. And here the order parameter space is the real projective plane. And this corresponds to the preferred local orientation of the rod-like molecules that make up the sample. And now because they're rod-like, they're like arrows without heads. So therefore, instead of using just the two sphere, we identify antipodes with each other. And this is just a definition of the real projective plane. And here you can see like examples of like pictures of these two systems. So here would be some sort of Heisenberg magnet system. So you have some continuous field of arrows. And here would be a nematic liquid crystal system. So you just have a continuous field of rods.
What is C in these cases?
Here we don't have C yet. C comes here. So a topological defect is basically like a connected component of C, the core, as well as the order parameter field it needs near vicinity. And okay, I have to point out that for the very introductory part, I'm gonna be extremely hand-wavy. So don't be too mathematical, because this is not like a correct it's not a definition in a mathematical sense. But for example, an archetypical example of a topological defect is this kind of hedgehog configuration in the Heisenberg ferromagnet. So you can think the physical extent is again just a three-dimensional Euclidean space, and then you take C to be the origin. And then for any other point of R3, you just put the arrow that points, the unit arrow that points outwards from the origin. So this gives a vector field that's well defined outside the origin. And this is like a topological defect because you cannot remove it by doing like a local surgery around the origin. If you cannot extend the field of vectors because of topological reasons. Basically because if you restrict it to any sphere that encapsulates the origin, the field on the sphere will be not null homotopic. So this hedgehog would be an example of a topological monopole. And topological vortex is a codimension 2 topological defect. Oh, this should be defect. So an example of a topological vortex is in a nematic liquid crystal is given like this. So here, again, you see the core. Here, the order parameter is not well defined. And in every other place, I've sort of sketched a continuous field of rods here. And as you can see, when you go around this core once, the rods make a 180-degree turn. So here it's really important that we sort of don't care about the direction of the arrows, only about sort of the rods. And this would be like a topological vortex in the nematic liquid crystal system. And it's been understood for quite some time that the homotopy groups and homotopy theory more generally is useful for understanding these defects. So if we have a vortex like topological vortex like this, or rather the core of a topological vortex like this, then you can just, choose a base point in X outside of C, and then take a path around the vortex. And then this gives you some sort of loop in the order parameter space if you just compose it with the field, the order parameter field mapping. And in fact, for a vortex to be topological is equivalent to this kind of thing mapping to a non-contractible loop in the order parameter space. Basically, because if this loop is contractible, then you could extend this field around here, and then it's not topological. You just make some local small surgery. And in fact, after you fix base points, then sort of the local vortex types are classified by the elements of the fundamental group of the order parameter space M. So if you get different elements here, you basically have different topological vortices, but yeah, I mean it's a bit more complicated than that, but that's basically it. And non-Abelian vortices, on the other hand, are things that occur when you have non-Abelian fundamental group. So there something sort of remarkable happens, namely that you have two vortices here, as you can see, and they correspond to, or they are classified by fundamental group elements alpha and beta. And now we assume that they do not commute. Then if we try to make this pass, or these vortices sort of cross each other, it doesn't work. For purely topological reasons observed by or deducted by Poinaru and Toulouse in like the 70s, there has to be a chord that's formed between them. And this basically corresponds to the commutator element in the fundamental group. And this is basically the kind of phenomena that are ultimately responsible for the existence of these stable tangled structures. Because you see, if you have a knot, for example, and if you can make everything cross, if you can make crossing changes, then you can unknot the thing, because you just, yeah, it's really easy. But if your knot has some sort of protection in this fashion, then you cannot do it. So let us now fix sort of more the mathematical setup for this talk. Again, the physical extent of the system is just the three-dimensional Euclidean space. Secondly, C, the core, for us, it will be just a disjoint union of smoothly embedded circles. So in other words, it will be a link. And M, we made the following assumption on the order parameter space M. We assume that its second homotopy group is trivial. This will be important for us to make some nice reductions, which I will explain soon. And then, of course, the field, the order parameter field, so the mapping from the complement to M is allowed to evolve up to homotopy. I mean, that's what you would sort of imagine, I guess. It's very natural. But what actually makes this thing interesting is that also the core is allowed to evolve. So it's allowed to evolve up to smooth isotopy. That's not so interesting. But the interesting part is that it's actually also allowed to evolve up to local surgeries that are topologically allowed. So that's sort of the interesting part. Because if you didn't allow this kind of thing, then you would just be computing the homotopy or the the homotopy types of maps between these two spaces, and that's not so very interesting maybe, but this problem is more interesting mathematically. So the reason for the trivial pi2 is that actually the complement of a link in R3 has an explicit description as a two-dimensional CW complex. And then you can just use some basic homotopy theory to argue that if your order parameter space doesn't have second homotopy group, then the homotopy classes of maps from the complement to M are in bijective correspondence with group homomorphisms like this. So this would be like the link group, sort of the knot group if C is a knot, and this would be the pi1 of the order parameter space. Yeah. And of course, okay, this is like the pointed homotopy classes of maps, but the unpointed ones you can just sort of conjugate. And the point here is that this data admits combinatorial description. So we can sort of recall very quickly that the fundamental group of a link complement admits a combinatorial description. So you just have a diagram for the whole thing. Okay, that's fine. You have this part here. And then the fundamental group has a presentation where, for every arc of the diagram, you draw this kind of arrow going under this strand here, which basically just corresponds to this kind of loop. So you pick a base point above the plane of the picture, then you sort of go down from there to the back of the arrow, you go under the strand, and then you come back. This is a loop. So it turns out that these three loops here would generate the whole fundamental group. And moreover, there's a very simple set of relations called the Wertinger relations, and you get one for each crossing. So basically, you form this kind of commutative square, and then you want that these two things are the same in the fundamental group. So it's basically because both of them correspond to the path that just goes, here and then goes diagonally under this place. And okay, we know the presentation for the fundamental group, and therefore we know the presentations for homomorphisms from it. This is just like a universal property thing. So you take the same picture, but now you label these arrows not by abstract symbol alpha I, but you just label them with the elements of the fundamental group of the order parameter space. So basically the idea is to record the images of this abstract element alpha I under this induced map on fundamental groups. And this describes a valid homomorphism if and only if the analog of the Wertinger relation holds. So for example, this equation here, which is just obtained from this one here by replacing every alpha with G. And just a remark that such a data is sometimes called like a pi1 mm representation of, or a coloring of this link. So this goes back to Ralph Fox's paper. Okay, so this is how to combinatorially describe homomorphism from between these fundamental groups. And we already observed a couple of slides back that this actually describes the whole order parameter field. So we have obtained a completely combinatorial description for the order parameter field. So that's pretty neat. And we now sort of also clarify what we mean by topologically allowed local surgeries. It's basically anything you can do locally that makes sense. Again, I have to apologize for such a hand-heavy thing. I will be more rigorous in the next part, because then I can actually just enumerate all the possibilities. But for example, what should be allowed is this kind of thing. You have two strands, and they correspond to basically the same element, but they go to the other direction. So you can think these things go closer and closer together, then they annihilate in the middle, and you get this part here. So this would be like a local reconnection. Another thing that should be allowed is that if G and H commute in the fundamental group, then we are allowed to make this kind of strand crossing. So they change sides. So, and basically, every time you're free to do something, that makes sense topologically, you can do it. Just don't do something super weird, like adding extra loops or, yeah, it's not a definition, but there's a better definition coming. Okay, so this was like the very hand-wavy and weird introduction to topological vortices. So now that I've bored all the topologists and confused all the rest, let us move to some concrete examples. So a fundamental role in this talk is played by the quaternion group. So I guess everyone knows what the quaternion group is. You just have plus minus one, plus minus I, and so on. The group law is given by the multiplication of quaternion, and it's actually a subgroup of several physically relevant order parameter spaces. So for example, the cyclic phase of a spin 2 Bose-Einstein condensate, the order parameter space is closely related to the space of tetrahedral orientations. So you basically have just a field of tetrahedra somewhere or in the space. And well, there are 3 different axes of the tetrahedron about which you can make a 180-degree turn that is a symmetry of the tetrahedron. And these sort of 180-degree rotations correspond to the elements I, J, and K in the quaternion group. One thing to note here is that, okay, you have the 180-degree turn or rotation, but it also matters in which direction you start to rotate it. So here we rotate it in one way, and if we would do it like the other way, then that would be like minus I. I mean, of course, it's like you have to make a choice which direction is I, which is J, and which is K, and then which is minus I, minus J, and minus K. But it's that part is sort of okay. And yeah, and this is like a really cool picture, but I mean, it's not something you could use to make any useful analysis of anything.
I and J completely looks the same.
Oh shit.
K is different, but
yeah, that's true. I probably just fucked up something when I made the picture. Yeah, it should be different. Anyway, so instead of using this kind of pictures with basically, I mean, they look nice, but they would be messy if you had a link and then you had a bunch of these fields going around them. Instead, we use the data of a bicoloring like this. So a Q8 colored link, the data of a Q8 colored link is basically, we will record it using this kind of bicolored arcs. And so what's the idea here? It's like you have, for example, the red and black arc would correspond to the element I in such a way that, if you go under the arc from the black side to the red side, you get I. And the role of the bicoloring is that it keeps track of the direction. If you go the other way, so if you go, the arrow went this way, you would get minus I. And I mean, it's similar for J and K, perfectly similar. And for this talk, we will completely ignore the vortex type that corresponds to -1 because it lies in the center of Q8 and it cannot therefore partake in any interesting topologically protected knotting. I guess it makes some statements of the results slightly more complicated because you have twice as many cases, but it's like a triviality, really. So we basically have we only consider these three kinds of loops or arcs. And okay, any kind of coloring of the diagram is not valid because you have to satisfy the vertical relations, as I mentioned previously. And luckily, these admit a really nice graphical depiction. So if you have a crossing of different colors, then the undercrossing by coloring flips. So as you can see, the green and the black color swap sides. And if you have a crossing with a single color, then you don't have a flipping. Nothing interesting happens. And as long as your bicoloring satisfies these things at the crossings, it describes a valid order parameter field. Moreover, these local surgery rules admit also a nice description. So, or nice graphical description. So first of all, they can only occur between strands of the same color. So therefore I only have green here. Of course, you have the same picture for red and for blue as well. And so the cases are basically like this. So because the green strands, they correspond to commuting elements in the fundamental group in the Q8, they are allowed to cross each other. So this is like the crossing change. But then you also have topologically allowed reconnection. So you can reconnect them in this way without creating any problems. And here the important part is that you cannot do the other way around, because that would create a discontinuity in the middle of the strand, and that's not allowed. So if we try to connect this to here, in the middle of the strand, you would have to flip the bicoloring, and that's not good. So that's one of the cases. And then the other cases is like this. If you have black against black here, like this, then you can just bring them closer together and they sort of annihilate in the middle, and then you end up here. So this is like a really nice description for the topologically allowed local surgeries. Okay, so now the question is so now we could ask that how easy it's actually to detect if a linked structure or a knotted structure is topologically protected, meaning that it cannot be unlinked using topologically allowed strand crossings and local reconnections. And we could, for example, ask the question about this thing here. So can we actually just unlink it somehow? And I mean, it looks pretty stable, right? Because, you know, each of the crossings, you cannot really do anything here. You cannot do anything here. You cannot do anything here. It looks a bit like, yeah, maybe it's stable. Maybe it cannot be unlinked. But unfortunately, you can unlink it. So you just pull this blue thing closer to here, then you perform a locally allowed surgery here to end up here. And now we can see actually these are unlinked. You can just pull the blue thing out. So this means that this link here is not topologically protected. It can be unlinked using topologically allowed surgeries. So for this reason, we need to construct invariants for Q8 colored links, just to be sort of certain when something is topologically protected. And so the most obvious thing you can do is consider the linking invariant L. So if you have a Q8 colored link, we define its linking invariant as the total Gauss linking number between the red and the blue loops modulo 2. So that might sound like a little bit odd, but actually it doesn't depend on the pair of colors that are chosen. This is not hard to prove, but I'm not gonna discuss this here. And this has another description. It is the number of times a red loop passes over a blue loop modulo 2. So it's something that you can just look at the diagram and you can just immediately count it. So the equivalence of these two is like some fact about degrees of maps, modulo 2 degrees of maps. And moreover, it's clear that it remains unchanged in these topologically allowed local surgeries because they only occur between strands of the same color. And here we do things only, or count the crossings where there are different colors. So for example, using the linking invariant, we could conclude that this thing is topologically protected. Indeed, the number of times the red loop passes over a blue loop is 1. This is the only place. So that's pretty easy. However, there's another invariant which is way more refined, which takes, well, not way more refined, it's like twice as refined because it takes values in Z4 and not Z2. And interestingly, it basically provides a complete classification for these links up to topologically allowed surgeries. And so what is this invariant, basically? So, okay. We have to start with defining the alpha invariant of a loop in the diagram. So for us, let L be a red loop in a Q8 colored link diagram. Of course, you can do the same thing for green and for blue as well. We just fix red for ease for us here now. And so the alpha invariant is defined like this, where the alpha of L is I to the power of omega, where omega is the right of the loop. So, or the self-right of the loop. So it's something you can sort of compute from the diagram here. And for Q is sort of the important part of the definition. So how it's obtained is basically, okay, you choose a base point on your red loop, and then you start going to the direction where at first black is on your right side. So you have to fix this kind of orientation convention. So therefore here we would go here. And then at each undercrossing, we sort of record the quaternion that we obtain. So the blue color corresponds to K, and because we are going from blue to black, it's actually minus K, both here and here. So the Q would actually be just minus K squared. And here we do the same thing. And okay, here we get K. We're going from black to blue. We get K again, but then we get minus I, sorry, because we pass under red. And basically the Q will be this part here. And because this thing is actually trivial, as we saw before, it should have like a trivial invariant, and indeed it does because of this right thing here. So basically the role of this term here is just to fix potential problems with the particular diagram that we chose. Okay, so it's not difficult to show that this alpha L doesn't depend on the base point and that it is a power of I for a red loop. And therefore it's like a well-defined invariant of the diagram. And how to define the red Q invariant is the following thing. So you basically go over all the red loops in the diagram, you multiply their alpha invariants together, and in a perfect world that would be fine, but we have to fix things again. So you have to take -1 to the power of L red, where L red is the total pairwise linking number between red loops. So for example, here, you know, the alpha invariants here are like 1 and 1. You just do the same thing here, and the computation is here. But because these red links here are linked together once, the order part or the Q invariant is actually 2, because you get -1 contribution here. Oh yeah, note that it's the exponent variant, and that's defined modulo 4. And why do we want to keep track of this? Well, because this crossing can be removed, right? You can just make these pass through each other, and then basically what happens after that is you remove the i's in both of here, and then you have just -kj, and that's I, and then you get I squared and no contribution for here, so you get -1. So this is just fixing, or the role of this thing is just to, make this invariant in this kind of strand crossings. So as you can see, I mean, it's a bit complicated, but it's very elementary, the definition of the invariant. And now, okay, we have to show that this is actually an invariant not of the Q8 colored link diagram. So we have to show that it's invariant in these Q8 colored Reidemeister moves. Because, I mean, every diagram of a link is related to every other diagram by Reidemeister moves. And if you have Q8 coloring, then there's basically a unique way of making these Reidemeister moves into Q8 colored Reidemeister moves. And I'm not going to go over the proof in detail, but I mean, as you can see, it's pretty easy. Like, for example, here, we just add this kind of thing here, but these introduced things, contributions to Q, actually just cancel each other, because here we get -k and then here k, and that's the only difference here. And all the other proofs are easy, like in the same way. And that's actually pretty nice. So we know that Q invariant is an invariant of the Q8 colored link, not just the diagram. And this actually graphical proof that the Brownian rings are a non-trivial link, because you can just compute the red Q invariant here, 2, not 0, and therefore it's non-trivial. I mean, if you just have a bunch of loops that are not tangled together, then there's no way of you getting a non-trivial Q invariant, right? Because you basically don't have any crossings if you choose the right diagram. So this is like a amusing sort of application. I mean, of course, this was known way before, but it's a nice proof. But the thing that we are really after is not just the independence in these Reidemeister moves, it's actually conservation in these topologically allowed surgeries. So this is basically the important part here. And so first we establish the invariance in topologically allowed strand crossings. And again, the proof is a bit, I mean, it's not very complicated, but it's a bit complicated, but it is very elementary. So you just analyze what happens when you make this kind of thing. So this is basically one of the 3 cases you have to consider, and then every time you just have to make some small computation, and that's the proof. I mean, I'm sure everyone in the audience could give the proof if they tried. The other thing is these topologically allowed local reconnections. And here we have, I think, 2 cases. This is the hard case. And again, you just have to sort of analyze what happens when you connect this thing in this way. And again, it's not very, I mean, it's elementary, but you have to sort of compute things, and yeah. And so that's sort of, I mean, it's not very conceptual, I can say that, but it's just something you check on a piece of paper and then you're sort of happy. And okay, so I said that this actually provides a complete classification of Q8 colored links, and this is like the really cool part here, because no matter how complicated your Q8 colored link is that you start with, if you just apply enough topologically allowed local reconnections and strand crossings, you will either reduce it to one of these three things, or you just unlink the whole structure, depending on the value of your Q invariant, which, by the way, doesn't depend on the color that you choose. Actually, I don't know any good proof for this. The only way I know how to prove it is first use the classification and check it in these cases. I mean, there's probably a nice proof for this equivalence here. But so basically, this is like the complete classification of non-trivial Q8 colored links up to topologically allowed surgeries. So you have these three looped chains of length 3, and then the Borromean rings with this specific bicoloring. And note that the difference between these two things, like the 1 and 3, is that you just flip the bicolorings. You know, all the bicolorings here. I mean, the important part is that you have to flip like odd number of bicolorings. If you flip an even number of bicolorings, then you can actually undo that. And so what is the idea of the classification? This is actually not so difficult. So up to allowed local surgeries, you have at most one loop of each color. You know, you just connect all the green loops with themselves and all the red loops with themselves, and then you have one loop of each color. Moreover, in this evolution of the system, each loop is allowed to cross itself because the color doesn't change. Only the bicoloring flips, the color stays the same, everything is allowed to cross itself. So basically, we can use Milnor's classification of 3-component links up to link homotopy as our starting point. And this is sort of nice classification because they are just classified up to pairwise linking numbers and the triple linking number, which is defined up to the greatest common divisor of these pairwise linking numbers. So if you combine this result by Milnor with this result that allows us to change the linking numbers up to a factor of, sorry, not a factor, up to an integer multiple of 2, you basically get the result. You can see, you know, you have this twice loop thing here, you just, you know, bring them closer, you make a reconnection, and then you can just move everything straight, and you reduce the number of crossings or the number of linking. I mean, you can just find some amusement here as well. If you reduce this Q invariant modulo 2, you actually just recover the linking invariant. Moreover, if you only have like one loop of each color, and if the linking invariant is 0, then this Q invariant is actually twice the Milnor triple linking invariant. So in some sense, we almost have like a short exact sequence of invariants here. So the Q is, we somehow extend it by extending modulo 2 linking number by the modulo 2 triple linking number. I mean, of course, this doesn't really mean anything, but it's just an amusing thing to consider. Yeah, I guess this is not so important, but you could consider like the universal additive invariant of Q8 colored links. So you just take all the links up to all the Q8 colored links up to sort of equivalence, and you get some sort of universal additive invariant, much like some sort of K theory of these kind of things. And then we have basically proven that this is the universal additive invariant. And yeah, one sort of physical remark is that, okay, we obtain a finite classification, and usually these classifications of knotted vortex structures are like very infinite, because they don't consider these allowed local surgeries. So there's infinitely many knots and links, so there will be infinitely many vortex knots as well, like even more than just the number of links. So this Q8 colored links was a really sort of nice story, sort of almost perfectly understood. But the next thing is like tricolored rings, and that's something I studied before Q8 colored links, but it seems to be more complicated. So the results are way less complete. And so here, the fundamental group of the order parameter space is isomorphic to the symmetric group on 3 letters. I don't know any topological, any physical system which would give rise to this kind of order parameter space, but I mean, I haven't looked very hard either. So probably there's some system. And so what is a tricoloring of a knot? It's basically, you describe the sort of order parameter field where the vortices are classified by transpositions in sigma 3. So, you know, red would be like you swap 1 and 2, green would be you swap 1 and 3, and blue would be you swap 2 and 3. And this is actually the original way how Ralph Fox came up with the idea of tricoloring of a knot. And the crossing rules are quite simple, namely, at each crossing, either you have only one color or you have all 3 colors. So that's enough to describe the whole thing. And also, like the sort of allowed local surgeries is like super easy to list, because you can do everything basically. I mean, these are all the reasonable things you can sort of do locally, and you're allowed to do any of them. There's no issues with like bicoloring and different directions working or not working. Just these things here. And again, as before, it might be difficult to detect topological protection. We start again with the knot here. It looks maybe locally that, okay, you cannot do anything here, you cannot do anything here, you cannot do anything here. But then actually what we are going to do is we pull these 2 things closer together, annihilate in the middle, and it's just a completely unknotted thing after that. So again, we are trying to construct some sort of invariant that would help us detecting topological protection. And yeah, this is the most important part. I mean, the whole problem is sort of solved if you just stare to this picture for some time. Namely, you know, there's 2-handedness for the trefoil knots. And if we take 2 trefoils with different handedness with this tricoloring, then actually we can connect these 2 things here. And this is the situation we started in the previous slide. So this is like, you can unlink this. However, if we put 2 trefoils, tricolored trefoils in the same picture with the same handedness, then something weird happens. So, okay, we start the same way. We connect these things here, okay? Then we make like a local reconnection between these 2 things to obtain here. Then we pull this one down and we are here. Then we pull this one down and we're here. So we got the trefoil. But it has a different handedness. So we started with 2 left-handed trefoils, and this is a right-handed trefoil. And yeah, so you can sort of make deductions from this. So we should look for some sort of an additive invariant of tricolored links that takes values in this integer modulo 3. And it should be able to distinguish between the different orientations of the knots. So it should be some sort of oriented invariant. So what do we do then? Well, first of all, a tricolored link with the core C is just classified by this kind of map. I mean, this is sort of trivial. So we compactify the 3-dimensional space to a 3-sphere. We take the core away, and then this is basically just classified by the map between the fundamental groups. Okay, and then the classifying space of the cyclic group of order 3 is actually a double cover here. So you can pull this thing back. You could to obtain some sort of a double cover of both of these. But then, because it's a tricolored link, you can actually fill this missing part. See, so we take like a double branched or double cover of this S3 minus the core minus the link or the knot, and then we can actually fill that thing in the branch or in the cover. So in that way, we obtain a branched double cover X of S3, which maps in this way to the classifying space of Z3. And actually here, okay, S3 is an oriented manifold, and this gives a canonical orientation for the manifold X. X is also a manifold. So now we have a continuous map from a complete oriented manifold to the classifying space of the cyclic group of order 3. And we define the invariant to be this thing in the oriented Bordism group of the classifying space. So that's our invariant. I mean, I tried to go through like all the knot theory invariants, and none of them seemed to work, so I had to figure out something new. But this is like really cool. And okay, then you can just compute with Atiyah-Hirschberg's spectral sequence. Like, it's a really easy computation. You don't have to analyze any of the differentials. That this Bordism group is actually just a singular homology of that thing, and that's isomorphic to the Z3. So at least the group our invariant lies in is the same that we expected. And okay, this was, I guess, originally written for Ben Williams, this remark. It's something, okay, maybe this is like not the right way to do things. Maybe you should have to consider some sort of stacky things, but it's not important for here. And okay, we have to sort of consider, or we have sort of defined the invariant, but we haven't proven that it's actually conserved in these allowed local surgeries. And as you can remember, there was many of allowed local surgeries, but actually we only have to check this one because all the other ones reduce to it. So for example, if we want to do strand crossing from this to this, we can just do this one here. So we pass to here, and then we can just, twist this to the other way and undo the whole thing, and then we end up here. And it's not hard to check that this one preserves the cobordism class because you have some sort of saddle cobordism between them. Okay, so that takes care of the sort of well-definedness of this invariant. And the last thing to do is actually, we want to show that these tricolored trefoils are non-trivial. So we have to compute something. But it's well known that the branch double cover of the trefoil is homomorphic to this length space. So it's just like S3 modulo the cyclic group under some action, the cyclic group of order 3. And then you can just apply the Sir spectral sequence to this homotopy fiber sequence here. And again, it's an easy computation. You don't have to really analyze any of the differentials because anything that's sort of relevant dies for trivial reasons. And then you can sort of compute that actually the generator of the third homologic group of the length space, and this is, by the way, isomorphic to Z because this thing is an oriented manifold, so you just use Poincare duality. So this thing here pushes forward to the generator of this thing here. In other words, it has a non-trivial invariant because, I mean, the map from this to here is basically you just push forward the fundamental class of X to this group here. So we just computed that, okay, the class of the trefoil, tricolored trefoil, actually pushes forward to the generator. And then, of course, this holds for both of them. And they actually map to the sort of the opposite elements because they are related by the change of orientation, which is like multiplying by -1 in the homology. And we have concluded that the tricolored trefoil has a non-trivial I invariant. So we have sort of shown that, or we have shown that these tricolored trefoils are topologically protected against decaying by these color preserving local surgeries. And unfortunately, this is basically how far it goes, the knowledge about this. So for example, it would be interesting to consider not only tricolored links, but more general sigma tricolored links, where the cores would correspond to something else as well than only the transpositions. So, for example, you have the only other non-trivial elements here are the cyclic permutations of order 3. And so it would be interesting to have invariants in this case as well. And one remark is that I've looked at many examples of these tricolored links, and it seems that everything can be reduced to one sort of tricolored trefoil, at least a small example. So maybe this Z3 provides some sort of complete classification of these tricolored links. Who knows? And yeah, I'm done.
Thanks, Toni. Yeah, thank you very much. It was very interesting. So any questions? I have one question. So you already said that the in the Q8 case everything is understood, but is there like a does the cobordism idea apply also for the Z2 invariant? Do you have something similar?
I think you might be able to get the linking invariant using this kind of cobordism idea, but trying to do this Z4 valued Q invariant, it doesn't seem to be working. There are some problems when you try to do this kind of construction. So yeah, I mean, yeah, because I did this case first and then went to Q8 color diagram. So of course I first tried this strategy there, but for some reason it didn't really work.
Okay. Well, I'm not asking how we got the cobordism idea. I think it's the benefit of working cross fields. Okay.
Yeah.
Yeah.
Doing a PhD in algebraic cobordism.
Okay. So any other questions? Okay. So if not, let's thank Toni. Thank you very much.
Thank you. It was a pleasure.